Okay. So hello everyone, my name is Jacob and I'm Senior Rendering Engineer at King Games, and I'm going to be talking about real-time global illumination in Enshrouded today. So first, I will be walking you through King Games and Enshrouded if you don't know that, and the benefits of dynamic global illumination and why we actually choose that. Then I will show you the building blocks which we have, which is the spatial cascaded cache and the science distance field trace which we have. Then I will show you the three types of probes which we have. They are the frustum probes, the world cache probes, and the ambient probes. And then I will do a full pipeline overview. At the end, I will show you spatial temporal sampling combined with our screen space reflections and the voxel volume for fog and some optimizations, of course. At the end, there will be a conclusion, and I hope we will have some time for questions because this is a rather long talk. So King Games is an independent studio based in Frankfurt, and we are around 70 people with 23 programmers, and out of that, 7 graphics programmers. We are mostly fully remote and have our custom tech since 2005 and shipped 38 games on all platforms. Enshrouded is our most ambitious project by far. It is a voxel-based survival RPG game with up to 16 players, which is in early access since January 2024. We already have over 3 million bought players over 3 million players bought the game. And we have 4 big updates already, which means that we have every 2 to 3 months a big update. We are currently only for PC, but the consoles are in work and will be available for the release. We are running exclusively on Vulkan right now, and one small heads up, there will be a talk from Julian Konen and Lucas Feller about Vulkan in Enshrouded later today about 16:30, so don't miss it. We have our custom engine, which is called Holistic, and we do C++ for everything we can. So why dynamic global illumination? Well, for us, it wasn't primary choice because we have a destroyable world. The player can toss a grenade, everything can change, instantly the light environment changes, you have to adapt to that. So there is no room for pre-baking anything. Also, it makes the scene feel alive, especially if we have dynamic weather and day-night changes as we have. It also makes our artists pretty happy because they are working in an environment which is what you see is what you get, and when they place some object into the scene, it automatically gets the correct light environment, and also, and is more important, contributes to the light environment. So every object is part of the light scene. So let's go over our building blocks. The first one is our spatial cascaded cache, which is a 32 by 32 by 32 world aligned grid centered around the player, and it has 12 cascades. This is how it would look like. We have 2 ways to activate these cells, and this is first by a depth buffer, and the second with a XYZ position buffer. Important to know is that actually when we're spreading this about the whole world, this is amount of probes or cells which we could never work with in real time. Therefore, we have a cap of 16,000, and we are keeping that all the time. We have a 2-meter spacing at the start, and we are doubling this spacing for each cascade. We are also garbage collecting inactive cells, so this is really a cache. So if you have a camera and your pen to the left and some of the cells are going out of the screen, they are not going to be deleted immediately. They will start losing quality. If you are managing to pen back again till they expire, you will just reuse them and they will not be resetted fully. So to the second building block this is our science distance field representation of the world and the science distance field race. It is a very much simplified version of the world, as you can see in the video, and you can see the different cascades switching from one to the other. So very, very small objects are absolutely not present in the representation, and median objects are only present at high and ultra settings. The voxel world is, of course, fully present. This is optimized for speed and, of course, very hardware independent, and this is also the major decision why we actually went for SDF race, because we could have, and we actually also had some prototypes with some ray tracing APIs, but we just wanted to be working with one version of the code on every other hardware which we can have. So this is what we went for. It is also very much scalable because we can choose the resolution of the science distance fields and also pick which ones of them we will be using for different hardware. Around that, there is a BVH acceleration structure to make it fast. So let's go through our 3 probe types. The first probe type is the frustum probe. This is using the cascaded cache, which I was talking about earlier. And in this case, we are using the depth buffer to spawn the probes or activate the cells on top of geometry. As you can see at the end of the cave, there is the cascade jump to the bigger cascades, and the probes are taking double the space. Each of these probes is, of course, shooting science distance field rays in all directions, and each of these hit points is then shooting another set of rays, science distance field rays, into the directional light, so sun, for shadowing. Also, for local global illuminants, we are actually also resampling the probes themselves when shading. We choose the octahedral encoding, which is a very efficient way to store a three-dimensional vector in a 2D space, and it's also very scalable. We are reusing it over the place. And there is still one thing to take in account with this, that if you want to sample an octahedral map, you have to create a pixel border by hand so that your sampler is actually wrapping nicely around. This is how an octahedral encoded radiance map would look like. For ultra settings, we are using 32 by 32. Then mid settings are 16, and low end settings are 8 by 8 for the radiance maps. But for irradiance, we are using 12 by 12 for ultra, and mid and low end is only 8 by 8. This is sufficient because this is diffuse lighting, and you do not need so much detail there. We are storing all of this in an atlas of 128 by 128, which is, again, these 16,000 probes which we can activate. On the top, you see the irradiance, and on the bottom, the irradiance atlas. So all the probes are actually encoded in E5 RGB9, so it's basically a UN32. And the distance, unfortunately, we had to encode it in float 16 RGBA because we need the precision when occlusion culling. All right, the second type of probes are the world cache probes. So far we had only probes in front of us, but these probes are actually shooting rays also behind the player or on other places which the Frustum probes were not spawned, and we still need to sample global illumination there. Therefore, we are spawning world cache probes at this position. These, again, shoot science distance field rays into the world and can resample each other for local global illuminants. They can also sample the Frustum probes, of course, if the ray hits some area where a Frustum probe is located. These are actually mutually exclusive. That means where a Frustum probe is, there will never be a world cache probe. So the technology behind that is absolutely the same as with Frustum probes, the only difference being that we have a resolution of 4x4. So this is, for example, how I said it is very scalable. We just say that this probe is 4x4, and that's it. There is no other change in the code. And we are encoding the irradiance as a spherical harmonic due to bandwidth reasons, but we will be talking about that later in detail. The cascaded cache, in this case, is a little bit denser, as the probes are very low resolution, and they do not store any occlusion at all. That means that we have to have them small so that they do not overreach walls and do not start leaking. So to show you how far such a two-level system would reach, I prepared a small animation. So on the right, you see the player, which is located in some labyrinth and looking at the corner, and therefore he will spawn a Frustum probe there. This Frustum probe will shoot a ray, and at this position we will get a world cache probe. So this is your first bounce, which will reach the player, actually. Then the world cache probe will shoot another ray into the world, and the hit position will be again shaded. We will be not spawning other world cache probes from here on. We are actually cupping the chain here, but we are still sampling the point lights and the directional lights. So at least for point lights, you have 3 bounces. For full global illumination, you have 2 bounces. So in this particular scenario, these 2 lights behind these many corners would actually contribute to the visible pixels of the player. The third type of probes which we have are the ambient probes, because so far we were only talking about the surface, and all of these probes were just spawned next to some geometry. So therefore we need something in the air too, because we have a lot of fog. So these are the ambient probes. It's another grid of 16 by 16 by 16 with 8 cascades around the player, and we thought about something very interesting here. And it is that we have all of these frustum and world cache probes, which are actually filling the whole world, and they were already shot. So we have basically a starting and end point, which means we have a line in three-dimensional space. So we thought that we will be reusing this information, and we intersect, so we do a fast voxel traversal and intersection with a bounding box, so line bounding box intersection, and then we fill the information of the radiance along the ray. So these probes are not shooting any rays, actually. They are again encoded in E5 RGB9, and we actually found out that we do not need to pick all the rays. It is enough when we pick randomly around 10% of the whole ray budget which we have. Of course, we accumulate all rays and calculate the radiance mean at the end that touched a certain probe and update its mean value. So how it looks like altogether. So these are the frustum probes. As you can see, they are not spawned beneath the cliff where the player doesn't see anything, but the world cache probes are spawned there because the rays are hitting there. And then we have the ambient probes around the player, the first cascade, and then iterating through all the cascades up until to the 8, which is a little bit special. So the last cascade is not centered around the player, but in the center of the world and covers the whole world and is used as a backup if everything failed. So let's get over the whole pipeline right now. At the beginning, we start with updating the frustum probe. So we have our depth buffer and we have our cascaded cache. So we will activate cells in this with this depth buffer in the cascaded cache. But since this is a world-aligned grid, a lot of probes will actually get stuck in some walls, so we will need to find a better sampling position. Since we have the whole world encoded as a science distance field, we can easily find the nearest surface position and make a push out. But this is still not enough, because if you would just let the probe very near a surface, you would get very much problems with occlusion because of the system how we are actually occlusion testing. You will see that in a second. So therefore, we are offsetting into the camera and a little bit into the normal direction of that surface. From that position, we can safely finally shoot rays. Of course, there is also the thing of probe quality. So if a probe is born absolutely new, we assign it the maximum number of rays, which is currently 512 rays, and then we scale it down very quickly up until to 16 rays, which is just checking around the surrounding for any light changes. And if it detects that there is actually a lot going on, it will crank up the number again. We recycle old probes, so if the quality reaches below 0, we'll delete them and new probes will come in later. We also register all of these active probes for all the indirect dispatches, because this is a fully compute-shaded pipeline where there is absolutely no jump into the CPU. Everything is on the GPU. So after we've got our ray amount, so this is basically just a wish from the probes, how many rays they would like to have, but we have a fixed ray budget, so we have to account for that. We just do a percentage comparison between the requested rays and the budget, and then scale all rays for all probes based on this percentage. This is still a lot of rays to fill, so what we do is basically each probe is writing its index into a batch index. This is how we call it. In this case, it is 16, but it is a variable, so we can change that. If we have, for example, more rays, it makes sense to batch them by 32 or maybe 64. So all probes are writing their indexes into 0, 16, 32, and so on. And then when we do a linear dispatch over the array, then each of these possible arrays will check one of these, so the nearest batch index, and get the probe ID out of that. When you have the probe ID, you know how many rays you are, and you know the first index of the first ray. Therefore, we can back calculate which exact ray index we are. And this is especially important because we will be generating directions right now. So we first actually started with uniform ray direction, but that was actually very horrible because we do not have the capacity to shoot too many rays, and with, let's say, 16 to 32 rays, you will have a very unstable probe which will flicker and will not propagate light very far. So we went for importance sampling and went for searching for the light. So how you do importance sampling is very, very easy. because you just need two things. The first is a weight by which you will be calculating your samples. In our case, that's the radiance of a pixel, and second, you need a sum out of that. So each probe in our case is calculating the sum of each ray, or of each pixel of its probe, and saving the sum in the probe data. Then for each ray, we just draw one random uniform number, multiply it with the sum, and we get a threshold. This is the dotted line in the middle. After that, we can consistently start marshing the pixels and accumulate the radiance values again up until a point when we reach the threshold or overreach the threshold, and this is our important sample. Very important here is that you have to be consistent, and you should always do basically the same every frame. But we found out that if we, for example, pick as a starting position the left upper corner and then march the probe linearly, it is possible that if you have a big light in the middle of the probe and a small light at the complete opposite of the starting point, you will never reach that point, because we are using blue noise for random values, and it's actually not very uniform. It has problems. So what we found is better, actually, is to consistently rotating the edge point. So we start with the left upper corner, then the right upper corner, right bottom corner, and left bottom corner, and start again from the left upper corner. So we rotate, so we basically merge 4 important samplings into one in the end. And that works very well and finds all the lights. So this is how it would look like in action. You can see that I will be moving the sun, and the probe will mostly hit only positions where the light is. All right, so now that we have generated the ray directions, we can finally sort. We are sorting by position and by direction. So let's talk first about the position. We are reusing the cascaded cache which we have, and we are just, when asking for an ID, just increasing the cascade offset, the cascade index by an offset. So what does it mean is, if you look at the image on the left, in the left bottom corner, this would be our probe, which we would like to sort somewhere into. So if we would increase the cascade by 1, then we would get actually a bin of the size of the blue block. If you would increase the cascade again, then we would get the whole red block, and if we do it the third time, we will get the whole green block. So we are having an 8 by 8 by 8 probe bin. So this is how it would look like. I'm moving the mouse and always targeting one bin, and all the rays inside a bin are shown. As you can see, these are pretty divergent. A lot of them are sky rays, a lot of them are going into the horizon and are super long, and some of them are hitting the ground and are super short. So this is not something that would really help when shooting, when we would just sort by the position. So we also do a sub-bin with, again, octahedral direction encoding with 4 by 4. And we can finally shoot. So after we have shot our first rays from the frustum probes, we have our hit positions, which can finally spawn the world cache probes. Again, the system is exactly the same. This is the same shaders, actually, which update the world cache probes. The only difference being that they are not offsetted into the camera direction anymore, but they are offsetted into their origin, because they came from some direction other than the camera, probably. Then we also populate, sort, and shoot them exactly as we did with the frustum probes, but there is a little trick here, and that is the ambient rays. I told you that the ambient probes are actually not shooting any rays, but it is not actually true. Because there is one special scenario where you do not have any frustum and world cache probes, and that's it when you are looking directly at the sky. Then you have no probes whatsoever, and all of these ambient probes would just starve. Therefore, we are detecting this, and if a probe sees that for a couple of frames it didn't get updated, it will request rays for the next frame. So these are the rays which were requested, so we group them together with the world cache and populate, sort, and shoot them all together. So when we have the hit positions, we can finally register shadow rays, which will be shot after that. And also, to avoid shader branches, we are separating everything into terrain hits, sky hits, and building hits, because these are 3 different shaders, and that hurts performance if you are putting them all together. So the shading function consists of these 5 steps. The first one is that we sample the emissive value from the voxel. Then we sample the directional light and also the shadow ray result, which we shot before. Then we sample point lights. We have a special cascaded cache for point light culling, which is called the light cache, and each cell in here is storing a list of lights which reached this position. So we are looping through this list and calculating the contribution of all the point lights. We have our own science distance field shadows, which are also checked here for shadowing. After we are done with the direct distribution, we can go on with the global illumination. So we sample the frustum probes if available, and if not, we also try to sample the world cache probes. All right, so now that we have shaded everything, we are finally able to blend and update our probes with new information. But let's first talk about variance. So in this example, I have a probe which is deep into a cave, which has absolutely no light source, so it's pitch black inside, and outside it's fully sunny without any clouds, so it's very strong light. Now, even if you would use the 32 by 32 octahedral encoding, which is actually already quite a lot, you would still have 11 degrees opening angle per pixel, which is for short distance quite fine, but for a couple of 100 meters, this starts to be a lot. And we have rays which go around a couple of kilometers, so you can imagine how much area such a pixel will cover. This gets even better if we have some emissive surfaces outside, which we have actually quite a lot. So we struggled with this scenario quite a bit up until a point where we found out the moving average estimator. So this is a two-level indirection system which is using the short-term mean and the long-term mean, and then a couple of other variables like the variance-based blend reduction, variancy and inconsistency, and also the short-term mean. Wait, sorry, that I already said. And this is not something we came up by ourselves. This is well documented in the Raytracing Gems 2019 book or 2018 Stochastic, All the Things talk. This is quite bandwidth heavy though. As you can see, we have the long-term mean, which is saved directly in the probes, which is just one UN32 because we are using E5 RGB9. But the rest, the short-term mean, the variance-based blend reduction, variance and inconsistency are actually 8 floats. So we are encoding them in flow 16, so in the end it's an UINT4. Together with the long-term mean, it's an UINT5, which is quite a lot. But since our radiance probes are actually the base for everything else which we will have from here on, we thought that this is actually worth the price. So for the occlusion testing and the distance blending, we are using a per pixel depth function. We are reusing the same rays which we already had, so we are not shooting any extra rays here. And we are clamping them to the spacing position or the probe cage, as we do not care about distances further away. And we are inspired by the variance shadow mapping approaches in SIGGRAPH 2021, Global Illumination Based on Surface, or Donnelly 2006, or DDGI 2019. All of the modern GI solutions are somehow depending on this system. Then when reading, we are using Chebyshev inequality, which is an efficient way to find slopes. And we are storing, therefore, per pixel mean and mean squared. This works very well in LDS, as you can preload all the rays into LDS and then just filter them in shared memory. But be very, very careful with ray guiding because this system depends on being constantly feeded with new samples. And if you do important sampling, you might just have 1 or 2 rays on one direction of the probe that would basically destroy everything. So we are doing uniform sampling after X frames, which is, in our case, 5 frames, and it keeps the system alive, and we have no artifacts whatsoever. So after we finally got all the radiance values into our probes, they are absolutely fresh and new, but they are still quite flickery. Even with important sampling, this was not enough. So we need to increase the samples. And increased samples means faster convergence to the information which you need and less flickering. So what we'll do is, again, important sample. We look at the area around the probe. And again, since we have the sum of radiance inside of a probe, we can again calculate the sum of all the sums inside of such a bin and then consistently marching this again drawing a random variable, and if we reach the threshold, then we have our sample. We of course do occlusion testing because we are not saving only the mean and mean squared, which is clamped to this spacing, but we are actually also saving the direct mean in the probe, so we have exact information about how far a probe actually sees. So we pick our candidates and then try to reproject between probes. Of course, again, when reprojecting between probes, we do reject samples which one probe wouldn't see because we have the distance saved in the probe. So this is how it would look like in slow motion. The yellow lines are actually the candidates which were picked this frame. The blue lines to the red crosses are actually the probes which were picked as candidates. I'm not sure if that's too visible. It is actually. In the middle there is a bush, and it should showcase that the probes which are selected are never on the other side. One important note here is that we are actually doing two reprojections. We are reprojecting the new rays from this frame from one probe to the other, but we are also reprojecting the history. These are two differentiators and two different dispatches. All of them, each of them is doing its own stochastic draw. And it is important because when we only reprojected the rays, since we are again important sampling, this is quite biased and was starving some positions, and other positions were overwhelmed with information and started flickering due to very divergent light information there. So what we also thought about is that we can reproject the history, so the long-term mean, but by doing so, you basically having a break on your convergence because you are reprojecting old values. So we are having a ratio here, so it's a ratio 4:1, 4 ray reprojections to 1 history reprojection, which keeps the probes very stable, then propagates light hundreds of meters into a cave, and is still very, very reactive to light changes. So after we finally blended all the radiance from our probes and from the neighbors, we are finally able to generate irradiance. This is a very simple approach where we are just taking a direction which we want to generate irradiance for, go through all the rays and cosine weight them, and at the end divide by the number of samples to match the irradiance Monte Carlo estimator. This is how irradiance probes would look like. They do not have too much of directionality, but this is exactly as you would expect from diffuse light contributions. All right, so now next to the blending of irradiance, we also have to care about specularity. So we have to pre-filter our radiance values. As we have stored direct radiance values in our probes, this would be already usable for perfect mirrors, but we need something for roughness bigger than 0.2. So what we came up with is basically a simple cosine-weighted blur and cosine-weighted downsample. We have different settings for different settings, and we have a ground truth mode which we compared against that and tweaked it so it is quite the same as in physically based renderer. Of course, it is not physically based, but it is very, very fast to generate. So these are the single levels where I'm skipping through all of the level, so MIP levels, let's call them MIP levels for the future. All right, so now that we have finalized our frustum probes, we can finally go to the world cache probes. Again, the system is exactly the same as in frustum probes. The only difference is being that the texture is just 4x4 octahedral encoded, and we have no pixel border because we will be never sampling this texture. We will be just generating irradiance out of that, so we do not need the pixel border. For irradiance, we picked spherical harmonics due to bandwidth reasons, because it has quite the same directionality as a 4x4 octahedral map, but with a 4x4 map, we would use 16 floats. In this case, it is 12, so it's a little bit smaller, and it helped with performance on low-end devices. Now that we have finally generated all our frustum and world cache probes, we are able to sample them. We have 2 screen space reservoirs, which are temporarily reprojected and spatially filtered, so denoised. The input for this pass is the irradiance probes, the radiance probes, and their respective MIPS, and the world cache probes, but just the spherical harmonics irradiance. contribution. And then the output is the screen space irradiance texture and the screen space reflected radiance texture, which was generated by reading out the roughness and interpolating between these MIPS. Again, both are encoded in E5 RGB9, so it's a simple uint32. So how do we sample that? That's very easy. We have a rolled space aligned probe grid, so we basically do trilinear interpolation. So in 3D, it would look like this. You have always 8 candidates, which you have to weight, and we are actually not sampling all of these. We are stochastically picking one of these candidates per frame based on the weight. The weight is a combination of the trilinear sampling value and the Chebyshev occlusion test. We also do a cross-cascade skipping. That means that we have a little bit of an overlap between the cascades, and then we have the start of the overlap, which is nearer to the player, and then the end. At the start of the overlap, the weight is 0, so we will always get the smaller cascade. In the middle of the overlap, it's 50-50. That means also the the cascade will be jumped with 50% probability, and then at the end, it's 1, so we'll only pick the bigger cascade. This makes a very smooth transition between cascades. So this is how a sampling cage is considering candidates, and you can see that the black probes are actually not considered, so there's no red cross inside of that. There is a reason for that, and that is that these probes are actually dead. They were spawned because the push-out told us that actually this is a good position, but since we have multiple corners, actually such a push-out can end up in other geometry. So we have to check if a probe is actually able to shoot rays. We do that by just summing the distance of all rays a probe was shooting, and if it doesn't cross a certain threshold, which is 1 millimeter, we know that we are inside a wall. These probes are still alive and shooting around 16 rays per frame, so that they still check if things maybe didn't change, because, for example, player could just pick a pickaxe and hit once there, and the probe would be freed. So for the hysteresis, when we are reprojecting from the last frame, we are basing this on roughness and the reflected movement vector. We denoise after that with Halton 3.3, and the weights for that are depth and the normal. For irradiance, we would actually not need to denoise because this is quite stable, but for reflected radiance, this is, so for the specular contribution, this is very much needed because you have a lot of high contrast lines and areas where there is a sudden jump from black to white. Therefore, we need to denoise to get a stable image. So now that we have generated our 2 irradiance and reflected radiance textures, we are finally able to call the deferred shading pass. This is necessary now because we will be still using screen space reflections to get information from this and combine that with the specular GI, which you will see in a second. So for the diffuse part, we are using a sample albedo divided by pi, right? So it's a Lambertian reflector multiplied by irradiance, but we found out that it's actually not energy conserving and hides reflections in certain scenarios. Therefore, we are having a roughness-based Schlick-Fresnel approximation where we are basically estimating the specular contribution and do a 1 minus specular contribution to get how much of the diffuse contribution we should actually apply. For the specular part, we are using split sum approximation, but a little bit more about that in a second. So stochastic screen space reflections, we are using them to get information from the scene which we do not have in the sound distance field because characters, for example, are not present in the sound distance field world. That means that we would never have reflecting characters in the game right now. We used the FFX stochastic screen space reflections library from AMD and modified it slightly to our needs. So what it looks like in combination, on the right top, you see the result of the screen space reflection marshing, and on the bottom, you see the specular GI result. We have to combine these to get the final image on the left. One thing, though, is that we still have the problem of 2 worlds. That means that the player is seeing, in this particular scenario, just some vegetation, and both rays which are highlighted are green. But there is also a probe above the head of the player, and it sees a completely different world. So this is quite a problem sometimes, but luckily we are actually interpolating between the GI and screen space reflections results, so it's never a hard cut, and it also usually no one notices. So after that, we can finally apply the specular reflections. So the input is the scene color combined with the diffuse GI already, and the screen space reflection marching combined with the reflected radiance texture. And we do a simple split sum approximation for the BRDF, and the output is specular contribution times reflected radiance plus scene color. So this is how it would look like on characters. On the bottom, you have just the specular reflections, and on the top, it is the final lit scene. So these are two mages, so it doesn't work only for metals. This is also for any other PBR materials. You can also see the walls, or the barrel is reflecting quite nicely. And all of this is just indirect lighting from this small opening in the ceiling. Now we are getting finally to the ambient probes. At first, we need to update them, right? So we are scrolling them, so we get the information from last frame and update its new position, and then we also do a visibility check. That means they are kind of occlusion tested, and only probes which are visible to the player are actually sampled, but updated are all of them. But just for these which are in front of you, we will be generating some extra rays to do a visibility check. So a visibility check is a very easy system where you are shooting just 6 rays for each probe into all the directions and just basically clamping your bounding box by that. This, of course, can have some artifacts if you have something very small in the middle of the probe and there is nothing around that, because the ray would hit such an object and would report that there is actually, so it would decrease the bounding box too much and would actually miss quite a lot of space. But we are not using these probes to light up fog and other effects directly. And when sampling these, we are jittering the position inside of each probe quite a lot, so this is actually not a problem. So as I said before, we are reusing all our rays which we have from the Frustum and WorldCache probes. We take around 10% of that and make use of the information that we have a start and end point in the 3-dimensional space and do a bounding box intersection with that. So this is again not from us, it's a ray marching algorithm which is linked below. And it's very fast actually. There is still one problem though, we cannot just simply blend in the rays because all of our probes are on the top of a surface, and in this particular case you see a Frustum probe on the surface. It's having it's hitting a ray on the bottom where there is, let's say, grass, therefore the contribution would be green and the ambient probe is colored green. On the other hand, we have actually a sky ray which hit the sky and got blue color, so we color all the ambient probes which intersect this ray with blue. And this is actually how it would really look like in game then. You would start running around and the ground would be green and everything above 1 meter around would start to be just blue. So this is not the way to go. What we actually do is we query the other side of the probe as we have the distances saved and extend the start position of the ray, and therefore we are able to apply the full range of green and blue to the whole area. So now that we have accumulated our rays, how we do that is again into an octahedral encoded buffer, because one probe could have thousands of rays intersecting it, and when we are accumulating it with an interlocked add, that would be quite a bottleneck. Therefore, we are splitting it into 4x4 and sorting by direction. And at some point, which is right now, we have to again group them together, so we calculating one mean value out of all of these rays, and then update one moving average estimator per probe to make the probes very reactive to light changes and still quite stable. But not stable enough. When we were flying around the world very fast, it was still flickering if you intercepted some very emissive surfaces, so we needed another in direction, and that's our voxel volume. So it is a 32 by 32 grid of the screen, which is then again subdivided into the depth with 384 slices for ultra, 256 for mid, and 128 for low-end devices. The distribution is not linear, it's actually taken from Doom, SIGGRAPH, and is very fast because you can pre-compute most of it on the CPU. From here on, we finally sample the ambient probes and have something to sample for the fog. And also, yeah, very important, this is very fast because before we were sampling 8 probes, again, like with the irradiance texture before, plus occlusion, which is very expensive. And since we have dynamic weather, which can be 7 to 10 kilometers away from you, we need quite some samples so that the weather still looks good. Therefore, we needed speed, and the voxel volume also gives us this because we are sampling just one UN32 instead of these 8 probes plus occlusion. Of course, it is temporarily reprojected, and the hysteresis is based on relative voxel movement speed to the camera. This is how the voxels would look like. In the middle, there's a cross representing the color, and you see that the spacing is getting a little bit bigger over distance. In this debug visualization, they are actually occlusion called, just so that I'm able to fly through them, but they are actually not occlusion called in the real game, because we found out that behind geometry, vegetation like trees, we would get some flickering. I know there are some techniques how we can tackle that, but since the whole pass on low-end devices costs around 50 microseconds, this is quite fine. So now that we have generated our voxel volume, we are finally able to sample it with fog. So this is how it looks like when you are flying very fast. This is actually double the speed of the fastest glider we have in the game. So this is nothing a player could achieve, and it's still rock stable and still has locality, so we are not bleeding the red part into the blue part and so on. All right, so let's get into optimizations. It looks like I'm on time, actually. This is great. So first of all, GI is very bandwidth heavy. So try to reduce bandwidth everywhere where you can. The Steam Deck was especially complaining about this, so we had to do quite some stuff here. We are encoding most stuff in E5 RGB9. This is a very nice format because it keeps grayscale values, and for the irradiance and reflected radiance values, as you could see, they were mostly whitish. So keeping grayscale is very important. It is also possible to directly load it into LDS and just decompress after you had them accumulated in a local data store. This is especially important on Steam Deck because it has very low shared memory, and therefore, it couldn't start too many waves and groups if we did not do that. Then we are ray sorting by roll position and direction and reusing the cascaded cache for this. We also sort our hit points into sky, terrain, and building. There's also design distance field models which we have, which I talked about earlier. They are currently not written here because this is actually a bug which we have right now. They are actually sorted into the terrain by accident, but this is something I will change on Monday. So, we have actually a fixed ray budget, as I said, and fixed buffer sizes for everything, and of course, adjustable settings for every system which we have. That means you can very easily just change a lot of settings by just editing a couple of lines of code. So conclusion, it is very much possible to write your own solid dynamic GI system nowadays. I think there is a lot of resources out there, a lot of open source code which you can pick and read through and just fuse them all into your custom solution, because we think that global illumination is very worth it and it gives your game some more dynamic and live. I hope that you could maybe learn something about the techniques which we are using, because they are very important, not only for computer graphics, but also for other areas. So we have our spatial cascaded cache, which has a very good spatial coverage and a very small memory footprint. Then we have our octahedral direction encoding, which converts a 3-dimensional vector into a 2D space and back very efficiently, and it can be scaled very easily. Then we have importance sampling, which gives you more suitable samples. You just need to know by what you want to weight. And the Chebyshev inequality, which is an occlusion test that can be easily filtered. Then the moving average estimator is very great for stabilizing your signal and keeping reactivity to light changes. And last but not least, the E5 RGB9 format, which is a simple and efficient way to store an RGB color into one uint32 and still keeping the grayscale values. So we are looking actually for a junior programmer. So if you feel compelled and you like Enshrouded, then please just grab us after the talk and we can have a talk. So if there are any questions, then this is the time.
So thanks, Jakub. We are definitely on time. We have 5 minutes for questions, and I'll be running around and getting them.
Perfect.
Okay, I'll try not to take up too much of your time, as I do have a litany of questions. One of the things that you mentioned was that you guys have a fixed ray budget, and towards the start you also mentioned that you have a metric for assessing, quote, probe quality, unquote, for determining this ray budget. Do you have any more details to share on that?
I'm sorry, I didn't understand the question. Can you speak a little bit louder?
Okay, so you mentioned that you guys have a fixed ray budget.
Yes.
And towards the start, you mentioned that you have a system for determining probe quality to kind of allocate the array budget. Could you share a few more words about that? What's your metric?
Yeah, sure. So our array budget starts with 100,000 rays for the low end, then goes about 250,000 for mid-range, and actually 500,000 for high-end devices. And the probe quality is very simple. You start with 0, and every frame you add a small portion. This is adjustable value, which we just played around with to see where is a good threshold, basically. So there is no mathematical formula behind that.
Okay, thank you. On the topic of culling, actually, you mentioned you also have a hard 16K limit on world cache probes. How do you determine which ones to call out and which ones to keep?
This is basically a push-through system. That means that probes that are actually too old will just get pushed out of that, and new probes will actually replace them. So if we are running out of space, we are actually increasing the rate by which we are making the probes when we are decreasing the probe quality. So if, for example, a world cache probe wouldn't get activated for a couple of frames, then you would each frame decrease its quality. And if we are running out of budget, we are basically cutting it right away.
One last more kind of open-ended questions. You guys mentioned a litany of techniques. It's a whole kaleidoscope. And you guys also do a lot of spatial reuse, a lot of temporal reuse. Did you guys consider using anything inspired by Restir in your systems?
Yes, that is actually something we are currently discussing because this technique has its limitations and is also, as you could see, we have a 2-meter spacing. Therefore, there might be some light leaking around, or not really leaking, but the specular contributions and light contributions will be a little bit bigger than you would expect. And therefore, we want to tackle that maybe with Restir in the future.
Okay, thank you.
Any more questions?
Here.
Oh.
Hey, great talk. I was curious, you're using SDF, cascaded SDF, but then when you actually get your ray hit, where are you getting your material properties from? Is that also encoded in a voxel grid somehow? Or
exactly, it's encoded in a voxel world, and we have some very optimized way to store that. I was not involved in that, so I cannot give you any details, unfortunately.
Right, okay.
But yes, we are querying the voxel world, and then out of that we get right now, the voxels are saving albedo, the normal we can get from the surface, then roughness, specularity is also there, and emissiveness, of course.
Okay. And for the importance sampling, you say you're doing a linear search through in order to find the the correct bin from your random sampling. Have you considered, basically making a summed area table and then doing a kind of binary search or something like that?
Not yet. Good idea. Thank you.
Okay, you're welcome.
I guess on Tuesday then, right?
Right.
Any more questions? Oh, yeah.
Hello, I would like to ask how you manage your sparse geometry. I noticed some trees in a trailer. Alongside this SDF, do you make your voxel semi-transparent if it hits the tree or something else?
Very good question. You are very sharp. We actually do not have anything for trees yet. So this is a big hole in our system. So if you are standing beneath some trees, your whole armor will be quite shiny because actually the tree above will not be represented. This is something we are working on right now, and we will give you a little bit of information. So for the trunk, I think we'll be just using voxels, but for the leaves, we'll be doing some volumetric thing that just decreases the radiance of the ray. But that's all in work. I don't have a final solution yet for that.
All right, one more question. None? Okay, then thanks for the speaker again.
Thanks for listening.